Hi, welcome to your lesson on the Pythagorean Theorem, one of the most famous theorems in mathematics. Let's get started. So let's begin with a right triangle, because the Pythagorean Theorem only applies to right triangles. A right triangle is a triangle with one right angle, like we can see here, which means a 90-degree angle. So what are these two parts of a right triangle called? Well, we commonly call them legs. Okay, there are more technical names for that, but let's go with legs. How about the side that is the diagonal one, the one across from or opposite the right angle? That side has a very famous name, and you probably know it. What is it? That is our hypotenuse, and that's the key to the Pythagorean theorem. So, big idea in mathematics. Pythagorean theorem is huge. Let's talk about it. Here is the Pythagorean theorem. When we have a right triangle with legs A and B, and hypotenuse C, this equation will always hold true. A squared plus B squared equals C squared. It doesn't actually matter what you call those letters, as long as you know that it's your two legs here, this, and here would be your hypotenuse squared. Okay, in words, let's break that down. The sum of the squares, the sum means addition of the squares, these squares, of the legs of a right triangle is equal to the square of the hypotenuse, Okay, so it's always important to know how words turn into mathematics. If you had these words, could you write that? The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. All right, let's do a little history here. The Pythagorean theorem is named after the Greek mathematician Pythagoras, who lived in the 6th century BC and is credited with the first recorded proof of the theorem. The theorem was known to some cultures well before Pythagoras. The ancient Egyptians knew about the 3, 4, 5 right-angled triangle. This is a triangle with sides 3, 4, 5, this is called a Pythagorean Triple. And they knew how to measure the right angle by stretching a rope with equally spaced knots. The Egyptian surveyors, called rope stretchers, used knotted cords to make measurements for building and restoring the boundaries of fields after the flooding of the River Nile. So there's some history of the Pythagorean theorem before Pythagoras. And certainly he inherited that knowledge when he came up with his theorem. So there's a TOK question for you here. Is it ethical that Pythagoras gave his name to a theorem that may not have been his own creation? What do you think? And of course our answers will vary, but we all have opinions on that. That's why it's a TOK question. Very open and open to debate. Let's do some problems with the Pythagorean theorem. But before that, let's begin with this 3, 4, 5 triangle that was just mentioned, the one that the Egyptians worked with. A triangle with leg 3, another leg 4, and a hypotenuse 5 is a good example of a triangle in which the Pythagorean theorem works. So let's take a look. 3. We know the Pythagorean theorem tells us to square the legs. Okay, so 3 squared. I'm going to literally visually draw that here. 3 squared is a square with sides 3 by 3, which has an area of 9. So that's 3 squared, 9. 4 squared. Well, we know 4 squared is 16, but let's visualize that. Okay, 4 squared means a 4 by 4 square, right? 4 squared. And that has an area of 16 blocks there. And the Pythagorean theorem tells us that this leg squared plus this leg squared equals a hypotenuse squared. Well, what is 5 squared? Here's our big 5 squared, 5 by 5 squared, 25 squares in there. So, does 9 plus 16 really make 25? Of course, numerically, but visually, does it? Okay, let's fill this space with these two squares, because that's what the Pythagorean theorem does. That square can fill this portion here, okay? And then we have 9 more red squares here, and you can, if you count along the edge here, there's 9 more squares. So, yes, truly, this leg squared plus this leg squared, in terms of areas, it fills this part here squared as well. So Pythagorean theorem works geometrically, not just with the numbers, but geometrically. Okay, let's look at that, the idea of these two squares filling this hypotenuse square in a different way. So I have a water spinner video. Check this out. This is a really cool thing somebody built, and we have a similar thing. So we have a right triangle here, and here is one leg and another leg, and we can see there's a square built off of that leg and a square built off of that leg. So this leg squared and this leg squared. Now, what's in there? There's actually a blue liquid in there. It's water with some coloring, I guess, and we're going to spin this thing and watch what happens. All right. So there's 2 legs squared, and now the water has a way to drain from those into the hypotenuse squared. And we know Pythagorean theorem works. 1 leg squared plus the other leg squared should give the hypotenuse squared, and look at that, perfect! It fills it perfectly. I think that's amazing. Great visual demonstration with Pythagorean theorem. This leg squared plus this leg squared equals the hypotenuse squared. Perfectly works out. All right, love that. Now they're going to go backwards, of course. Let's just watch this. This is amazing. This is worth that 15 seconds of your life for sure. Check it out. All right. From the hypotenuse squared back to the 2 legs squared. Perfect. All right, let's continue. Let's try some problems. So sketch this diagram in your notebook somewhere and solve for x using Pythagorean theorem. So you're going to begin with a squared plus b squared equals c squared. All right, let's see how you did. So these are going to be very simple. I know you've seen this theorem, but let's make sure we can get it right. Okay, 4 squared plus 3 squared equals x squared, our hypotenuse squared. 16 plus 9 equals x squared. That means x squared equals 25. And wait a minute, we just saw this triangle. We should have known this right away. And we take the square root of both sides. Square root of 25 is 5. We get back to that 3, 4, 5 triangle. One of these triangles called a Pythagorean triple. Okay. That was easy start. Let's try another one. Try this one here. Solve for x in this one. We're going to use Pythagorean theorem, right? Wrong! No way. That is not a right triangle. There's nothing there to show us it's a right triangle. There's no little square here to show this is a right angle. Maybe you saw it visually, but maybe you're thinking, hey, it's just a poorly drawn triangle. I'm going to proceed with the Pythagorean theorem. But no, it should not work. It only works for right triangles. Let's go to the next one. Okay, solve for x here. Use the Pythagorean theorem. Okay, in this case, our hypotenuse is known. So when you write equals something, that's not where the x goes. That's where the hypotenuse goes. So 12 goes here. And now we have x squared, this leg squared, plus this leg squared, 9 squared equals 12 squared. Let's simplify it a little bit. 9 squared is 81. 12 squared is 144. Subtract 81 from both sides to get this. So we have x squared equals 63. Now, of course, you can grab your calculator and find the square root of 63. And that is 7.94. I wrote that to 3 significant figures. Fantastic, that's fine. However, you should also be aware of a process of simplifying radicals. This is called a radical expression or equation here. We want to simplify that without going to our calculator or decimals. So you look at that number and you're like, can I break 63 down into 2 numbers, one of which is a number that I can take the square root of? Okay, so those 2 numbers are 9 and 7. 9 times 7 makes 63. And 9 we can take a square root of. So this can be simplified into, well, the square root of 9 is 3, and we leave the 7 under the root. So if you punch this on your calculator, 3 times the root of 7, you'd notice you get the same answer. It means the same thing, but this is a way to avoid going to your calculator, avoid going to decimal answers, and also to be more precise, because to write this, we had to do some rounding. Over here, no rounding. It's called a more precise answer. Okay, see if you can answer this. Determine whether a triangle with sides 6, 8, and 9 is a right angled triangle. Do those sides create a triangle that would be a right triangle? Here's how we check. Well, we check if the Pythagorean theorem works with these numbers, because if the Pythagorean theorem works, then it must be a right triangle. And you always begin with, well, what's our longest side? Because the hypotenuse has to be the longest one. In this case, 9. So I put that here in for c squared, and then that equals the 2 other legs squared. And let's check. Well, 9 squared is 81, 6 squared is 36, 8 squared is 64, so these 2 legs combined when they're squared make 100. And 81 does not equal 100. So these numbers do not work in the Pythagorean theorem. Therefore, if you drew a triangle with those lengths of sides, it is not a right triangle. Okay, because Pythagorean theorem would work if it was. Try a similar question. Sam has a vegetable garden. It's a triangle. And here we're trying to figure out, is it a right triangle? His garden, is it a right triangle? So try with these numbers. Okay, try the same process. The longest side goes here as your hypotenuse. We have our 2 legs squared here, and you check if this is a true statement. That equals this. These 2 equal that, but when you add those, they are not this number here. Oh, sorry, they are. I'm sorry. In this case, it works. If you add those, it does give you that number. So both sides of the equation are equal to each other, therefore it must be a right triangle. Great. Great job. Quick introduction or reintroduction to the Pythagorean theorem, and we will see you soon to practice some more.